Hello, everyone. My name is Jay Kinsey, and I'm here to talk about first LEGO League robot design judging and also this checklist as well. So, there are a couple things that are really important to the first LEGO League judging process. One of the things that's really important is consistency. Having a consistent judging experience between team to team is very important for the fairness for each team. It also helps in deliberations as well. This checklist really helps being consistent from team to team and looking at different parts of the robot while judging. So throughout the course of the day, you might see anywhere between 10 to 14 teams. At the end of the day, it's going to be very, very difficult to recall those first couple of teams. And such, it becomes very hard to stay very consistent when judging from team to team. In addition, a checklist like this is also really handy while in the deliberation stage. So at sort of a state level or world festival level, having very, very good notes on every single team is going to make making decisions a lot easier. So without further ado, let's kind of get into this judging sheet. This is not an official sheet by any means. This is just my thing that I've cooked up on my own. It is not supported. It is not endorsed by First in any particular way. This is just basically a shortcut that I use to take notes for myself. So even if you don't use this sheet, which is completely fine, having everything laid out here is still going to help you. And we're going to talk about each one of these sections, and we're going to look at different things that we want to keep an eye out for on the robot. So starting with the sheet, at the very top here, we just have some information about the team. So, for example, their team number, their pit number, their team name, their origin. For example, these could be pick your favorite team. The Wild West Robotics team, just making that up. And they could be team number 1527, and they might have a pit number of 6. And let's just say they're from Texas. I don't know, just making up this hypothetical team. So that's how you would use that, those areas. Room rank. So, during judging, you generally want to keep track of, where your different teams are standing. Generally, you would just keep them in a ordered stack as you go through the judging. And what you would do is at the end of that judging session, once you've agreed with your judging partner on the actual ranking, I really like to write the room rank there in the room rank area, just so that it's that those rankings are then attached to the team. And over here, we just have a little area where we can circle whether we thought the team was sort of fell into a high category, medium category, or a low category as well. I should also mention that one of the things I really like to do when judging is I like to carry a highlighter and a pen. And the reason why is because when you fill out these sheets, there's going to be a lot of stuff that's very similar, but there's going to be some things that are going to stand out. And having a highlighter is a great way to literally highlight those couple things that are making a team stand out. So, if a team is doing really, really, really well, I might circle high or highlight high. We can also put teams in for different nominations as well. So electrical elements. So here we are going to capture what the team is doing with the electrical elements. So a team might have, they might be using an EV3 brick. They might have so many large EV3 motors, so many medium EV3 motors, touch sensors, color sensors, gyros, etc. So you would just write in the number of sensors and things that they have, and you can circle what brick they're using. These days, it's very common for people just to use the EV3 brick, but it is very common for people to use the EV3 brick, but then also use like NXT motors, for example, or NXT sensors. So let's come down here to mechanical, and you'll notice the first thing we have here is the rubric. So this is the current first LEGO League rubric that I have slimmed down and put into this area on the sheet. And what that allows you to do is it allows you to not have to flip back and forth between your other judging sheets and this judging sheet. So this is just using very concise language Obviously, not using the full expanded language that First has on their actual rubrics, but this is just there to remind you as to what what those elements mean. So we're now going to talk about specific mechanical elements, and some of this can get really involved, especially on the mechanical side. So I'll try to go quick. So architecture, 90% of teams are going to be using a skid steer type system. So usually 2 wheels, 2 motors, 1 left, 1 right, and then just regular skid steer. Everything else is probably going to be less than 1%. So just keep that in mind. So dual differential drives. Dual differential drive it's kind of hard to explain, but you can Google it. It's where you use 2 differentials. One differential handles turning and one differential handles moving straight. It's a great way to gain extra mechanical precision on the table. Same thing with single axis drive. A single axis drive is another great way to add precision. And what that means is that the drive base is only capable of moving in one direction at a time. So I've seen some teams, they might have a set of wheels that they put down just to move in X, and then they put down another set of wheels just to move in Y, for example. I've also seen teams have robots that can only go straight or can only turn. So it's kind of like a polar method, you could say. Rack and pinion steering is what you would have in your car, that type of system. Synchro drive, extremely rare, but this is where each wheel can actually independently rotate on its axis and has power to roll. And then split bot is where the robot itself is kind of split into 2 parts. So you might have the EV3 or the programmable brick with some motors on one side of the table, and then connected by long wires might be another set of 2 motors that are running as kind of their own robot, but still tethered to the main robot, but they're doing something else on the other side of the table, for example. Drivers. So a classic question is to ask, why they chose the wheels that they chose. Actually, sorry, that's driver selection. Drivers are just what they're actually using. So, for example, they might be using wheels. There's a Lego ball caster that could be using treads. They might have passive wheels, skids, wheel casters, or something else. So you could just circle what they're doing here. Generally, it's going to be like a combination of like wheels and ball caster or wheels and skids, generally. Sometimes passive wheels too. So driver selection. So very common question. Why did you choose the wheels that you chose, right? And you can get a lot of answers from this. Some teams will tell you, well, we use these wheels because the directions told us to use them. So for example, the standard kit robot that you would get you would consider those directions. Some teams will say, well, we just tried different wheels and these wheels work the best. Intuition. Some teams will say that we just felt that these wheels should work better, so we chose them. Some teams will choose based on precision. Some teams will change or will choose based on speed. And believe it or not, some teams will choose wheels based on how cool they look. So just be aware of that as well. Some teams will also choose wheels for load capacity. So a really common thing that happens is as these robots get bigger and heavier, the wheels tend to compress, which changes the distance between the rotating axle and the ground. And so the robot will actually go a different amount of distance for the same commanded value, depending on how much the robot weighs. So there are wheels that are made out of a very hard rubber, and those hard rubber wheels have essentially no level of deformation in them. So some teams recognize that, especially for heavy robots, and so they might choose based on load capacity. And then finally, grip. Some teams might choose some wheels based on grip. So down here we have mechanical techniques and special features. So these are just extra things that they could be using or doing. So jigs. So these jigs means like alignment jigs. So a lot of teams use constructions or frames and things like that in order to position the robot in base consistently every time. Dedicated motor core. Dedicated motor core is this is really impressive to see. What dedicated motor core does is that it turns the entire robot into a giant attachment. So let me explain. You can have the the programmable brick and the motors all packaged together in one unit, and then that packaged unit then gets put into different bases. So it basically turns the whole robot into an attachment. Very cool to see. It's been used to great effect many times in the past. It can add some extra complexity, and there's definitely a little bit more in the programming, generally speaking, but it can be a really great way to go. Car transmission. So car transmission, I'm referring to specifically as a multi-ratio transmission. So, you might have teams that have, like a standard 1-to-1 drive, but then they have like a low range gear for more torque, for example, if they have to go up a hill or something like that. Power switcher multiplexer. So this has to do with how power is distributed through the robot. So for example, you might have a output on the front of the robot that maybe spins a gear or spins an attachment, but then there could be a lever or something like that the team throws that then powers something else on the back of the robot. So depending on how the how they switch maybe switch some levers or move some things will actually change where the power is going through the robot. Suspension. This is exactly what you think it is. This is like wheel suspension. Light sensor shield. So a light sensor shield is some kind of a covering that goes around the light sensor in order to block out as much external light as possible. Generally, doing this helps the light sensors be more consistent and accurate. Full wheel wells. So full wheel wells means that the wheels are 100% fully supported. For example, if you look at a standard kit bot that you get in the kit, those wheels are completely unsupported. So full wheel wells, means that there is a complete box that encloses the entire wheel. This eliminates any sort of flex that the wheels have, and it also increases accuracy because of that as well. Partial wheel wells are the not fully developed version of full wheel wells. This just means that the wheels are partially supported on the outside rather than fully supported on the outside. Stuffed wheels. So stuffed wheels is a way to make a wheel that is squishy harder. So there are a lot of squishy wheels that can be filled up with small Lego Technic parts like bushings and things like that. And filling the wheel with those bushings makes them harder and thus gives them more load capacity. So then we come to matched motors. So some teams will actually find out which motors are the most electrically identical. So they'll try to find motors that have the same behavior. They will spin at the same RPM when put under full load and things like that. There's several ways to build like test stands in order to match your motors, and they'll show them to you. But just be aware that that's something that some teams do, is they'll actually try to find motors that behave the same. And same thing for wheels. The people will try to find wheels that will roll the same. So you can imagine that I might have a wheel that was, made this year, but they also have made, lots of wheels in previous years. And you might have one wheel that's 5 years old, 10 years old, worn out, been played with outside, stuff like that. And so teams will actually go try to find wheels which will actually roll the same. And so usually they have a long axle and they put one wheel on each side of the axle, then they roll it. And depending if which way the thing rolls, if it rolls off to the left or the right, they can tell if the wheels are going to be matched or not. So if it's tracking straight, those wheels would be matched. Wheels yoked. So the wheels yoked is basically adding some kind of limited slip mechanism between the two wheels. Sometimes it's just with friction. Other times you can do it with detent and gearing, but it's basically trying to have some sort of friction coupling between the wheels so that when the robot's moving forward, that the wheels are locking together and tracking together. So it helps you go straight. So we're going to move down here to the manipulator, and we're going to talk about arms. So there's two main types of arms. There's axial joint, so just a regular, basically rotary stick type thing, and then a translation and forklift. So those are the two main ones that are out there. And then the third option here is full modular bay system. So some teams, they'll have a modular attachment scheme where they can just take like something that's a standard shape and plug it in. And when they do that, they can have, anything attached to that modular base. So it could be an axial joint or a forklift, for example. Number of attachments. So a lot of teams are going to be using attachments to solve missions. And the team might say like, oh, we score so many points and we have 5 attachments, right? So this is a great place to just write the number of attachments. Some teams don't use any attachments. Some teams just have everything on the robot already that it will need. But some teams do use a lot of attachments. So this number can be as low as 0, but it can be as high as 10, for example. And then we come to the opposite concept, the number of detachments. So a detachment is something that starts on the robot, but then is pulled off. So that generally the reason why you would want detachments are because it's a lot easier for operators to pull things off of the robot rather than put them on when they're actually running sort of under stress and under the time crunch of the 2.5 minutes. Attachment connection methods. We have axle peg. So this is just regular axles and pegs coming together. Top load structure. And top load structure has been very popular in the last couple of years. Basically, people have been building these robots that look like Borg, B-O-R-G, Borg cubes that have some outputs on the top for gears. And they will make sort of a framing type system and just pop the frame on top of their robot. So that would also count as a full modular bay. But this specific idea of having a very rectangular, solid, or very cubical robot with a frame that goes over the top is so popular that I decided to put that in here specifically because undoubtedly you will see some robots like that. We also have active locking and passive locking. So there are attachments that just passively sit on top of the robot, but we also have some, which would be a passive attachment, and then we also have some attachments which will get placed on top of the robot and then have some sort of active locking system which actually holds them in. So these could be like some sort of spring-loaded latch or mechanism, for example, or some sort of toggling lock, something to actually actively keep the attachment on. And then obviously anything else. So connection speed, this is where you would rate if how fast it is to attach an attachment. So attachments that are very slow, 0 and 1. Attachments that are very fast, 4 and 5. So that's something to keep in mind. I usually put axles and pegs, the axle peg, for example, down here, at maybe a 1 or 2. But then stuff like top load structure and things like that would be sort of 3 and up, generally speaking. And then here we have sort of general mechanical complexity. This is where you can mark if a team has a very big complex system or if they're using something that's a lot more streamlined and simple. So you might have teams that are doing lots of really cool, interesting things, but the mechanical complexity could be through the roof. Likewise, you might have teams that are maybe doing a little bit less mechanically, but what they might be doing might be more elegant, for example, and they might have less mechanical complexity, so they might be down here. And remember, these ratings don't necessarily assign values to anything. It's just an observation. So manipulator special features. So we're going to talk about some special things that apply to manipulators. So pneumatics. Pneumatics are incredibly popular. Pneumatics have been used extremely effectively over the last several years. They're really popular because you can basically put power wherever you want on the robot at any time. Linear screw actuators. So linear screw actuators there's a prefabricated Lego one where it takes a circular input or rotational input and then moves linearly, but sometimes teams make their own using worm gears. Spring-loaded actuators. So this is exactly what you think it is. So anything that's spring-loaded, or pre-tensioned, or something like that would count as a spring-loaded actuator. Gravity-powered actuators. So gravity-powered actuators are powered usually by falling weights, and that falling weight then applies torque to an axle because it's on a spool, and then that torque then does something. It's very common to use gravity-powered actuators, for example, with deployable vehicles. Color-coded attachments and automatic attachment recognition. These two things go together, but they are not exactly the same thing. Color-coded attachments refers to color coding the attachments for operators. So, a given runner might say, okay, first we run the blue attachment, then we run the red attachment, and then we run the yellow attachment, for example. Automatic attachment recognition is usually done with a light sensor, and the robot will actually detect the color of the attachment that was put on top of it. So the robot will be able to tell if it has the yellow attachment or the blue attachment or the red attachment, and then be able to load and then automatically execute missions based on what attachments have been added. Attachment connection verification. So this is where the robot does some sort of routine to actually verify that the attachment has been correctly connected to the robot. So for example, this could be lifting an arm to hit a touch sensor. It could be, maybe there's a light sensor or something that has to see a certain value. Just anything that the robot does to verify that it does actually have the attachment correctly connected. Driven exovehicle. So driven exovehicle, very impressive to watch. It's where the robot is put in a larger frame, and then it can drive the larger frame. So the robot gets sort of placed in its own car almost, and then the robot, generally by means of having extra rollers and gears and things, can actually power this larger wheelbase that it was placed in. Very common to be used for going over harsh obstacles or for getting to certain places very, very quickly. Quick swap cabling mount. So there are teams that will plug and unplug motors and sensors during a run, and teams that choose to do that a lot will generally make some sort of mounting system to make it easier to put wires in and pull wires out. And lastly, we have deployable vehicles. So this means that the robot system is deploying some sort of vehicle which will go accomplish some other mission. So down here we have what I like to call particular praises. So for example, you might circle this if you thought the robot was especially robust, if they had good use of gears, clever mechanisms, polished design, elegance, high innovation, very robust attachments. Also notice how we have very robust robot and very robust attachments, because those are two different things. Fast attachment changes, consolidated attachments, and good passive manipulators. So now we will move on to the software and programming part of the sheet. And you can see here that the first thing we have is the rubric. And then we come down here to programming features. So here we have program environment. This lets you select through using EV3, NXTG, Robot Invention System, which is really old, RoboLab, or direct bytecode. These days, you might see teams also using other programming languages, and you could just write that down here in the notes as well, or you could write it over here in the margin. Motor acceleration control. So one of the things that can really help a robot move on the table is reducing the amount of slip that the wheels have when starting and stopping. So one thing that some teams can do is they'll have some mechanism and software so that they will start at a lower power level and then end at a higher power level. So this can be done in steps, and it also can be done continuously. So they might start off at 20% power and then immediately go up to 70% power, for example, with stepped ramping. Or they might have something continuous where it has to do with every couple of degrees, or for every degree, for example, it's adding power. Or it could also be done on time as well. Over here, we have also B and PID. This stands for binary or proportional integral derivative. So this will make a little bit more sense when we get down to line sensors down here, and then I'll come back and explain some of that. So let's move on to the optical stuff. So this is light sensor related. Are they using line detection? So for example, just detecting the presence of a line. Are they using line squaring? So that's where you have two light sensors, and one light sensor might come up and hit a line, and then you wait for the other light sensor on the other side of the robot to go hit the other side of the line. That way the robot's actually nice and square with the line. Then we have line following, and then sense field. Sense field is here for actually sensing a field condition. So if there are flags that are certain colors, or something might be present or not present, you can use a light sensor in order to sense the actual state of the field. This will vary year to year depending on what challenges are available. And then now we come to binary and proportional integral derivative. So in line following, but also for other means of control too, we have the idea of having different line following algorithms. The most simple would be binary. So if you see a light value that's underneath some cutoff or underneath a threshold, then you turn one motor on, and if it's above the other threshold, then you turn the other motor on, right? So binary, your motors are either on or off. PID refers to proportional integral and derivative control, and a lot of teams, more advanced teams, will use proportional. Some will use proportional integral, and some will use, very rarely as well, the derivative. Proportional control is just making a correction based on how off of the target value the reading is, right? So if you're just a small amount off, then the robot will correct proportionally a small amount. But if the robot is significantly off, then the robot will correct a much larger amount proportionally. Integral refers to adding up error over time. So if the robot is consistently, some level of light away from its target, the I term, the integral term, will grow over time and then will push the robot over into the target. And then derivative is trying to predict future error and then take some corrective action based on that. You can learn more by Googling, PID control and things like that. But you're going to see a lot of either binary stuff or proportional stuff, most likely with one or two teams at the most using an integral term as well. And PID doesn't have to just be used with light sensors. It can also be used with many other sensors and other ways as well. So that's why I have it here sort of for everything. Ultrasonic techniques. So ultrasonic ranging. So this is just going up to, stopping in front of something and saying, okay, the obstacle in front of me is 6 centimeters away. I want to advance 6 centimeters. That's all that is. Wall following. So ultrasonic wall following is where you have the light sensor or ultrasonic sensor hanging off of the side of the robot, and then the robot can actually move down the field and look at its distance away from the wall and keep the same distance as it moves. Sense robot is kind of like sense field, except instead of sensing a field condition, it's sensing a robot condition. And the reason why I have sense robot here specifically in ultrasonic is because I've seen some teams with forklifts use an ultrasonic sensor to measure the distance their arm is off of the table. So it's specifically there to sense a robot condition. And then we also have sense field, so we can sense the presence or absence of, something in a certain area. And then you also could have binary or proportional integral derivative control as well. Gyro. So the gyro is one of these things that's very finicky. A lot of teams have a lot of issues with gyros, but some teams, can figure it out and get it working. And we have here a couple of different techniques that can be used. The first is gyro turning. So you can use a gyro to help ensure that you're turning a specific number of degrees that you want. And then gyro straight. So you can use a gyro to help the robot move in a straight line. So if the robot's starting to veer off to one side or the other, the gyro can actually detect that and then help correct for that. Very rare, but I've seen it done. Curve. So if the robot, for example, can make a radius curve, the gyro can be used to aid in maintaining that radius, for example. And then ramping control. So there are a lot of teams where they will use the gyro in order to track how fast they're moving and then use that to control how fast they're starting to turn and then ending to turn. It's kind of like continuous motor ramping, but you're doing it with the gyro and you're doing it while, generally speaking, turning. Touch techniques. Touch sensor bumper. A lot of people also use touch sensors as program starters, limit switches, or to sense a certain field condition. Now we're going to move down here to programming special features. Master control program. Very common among sort of mid to high level teams. A master control program is a program that will run all of the other programs. So it's a lot easier to have one program that's running all of the other programs rather than try to manually select which program you want to run, for example, out of the hierarchy file system. Multi-threading. So multi-threading refers to doing multiple things at the same time. You will see this sometimes where as teams approach a challenge, the wheelbase and the arm might start to move at the same time. Or the robot might be backing up and an arm might be moving up, for example, while it's picking something up. That's multi-threading. They're doing actions simultaneously. Stall timeout detection and stall timeout action. Stall timeout detection is detecting if the robot has stalled. So for example, if the robot runs into a wall and if the robot has not reached its target within a certain amount of time, it can air out and then move on to the next action. So that's what a stall timeout is. So for every movement, it actually knows how long it should take. And if it takes beyond a certain level of value, it'll automatically move on. And then stall timeout action is the continuation of that idea where instead of just going on to the next action, it can actually do a programmed sequence in order to correct for that stall timeout. So you could imagine a robot trying to move onto a wall or move onto a wall or something where it might get stuck somewhere, and so you might have it where it pulls away and then tries something else depending on if the stall timeout action has happened. Backlash compensation. So the EV3 motors have more backlash in them than the NXT motors do, and that's because LEGO changed the mechanical packaging. And because of the change in mechanical packaging, there are more gears, and more gears is more backlash. So some teams have done backlash compensation where they will essentially blip the motors in the direction that they're going to go. A very low power level, but enough to just move all of the gears so that they're now running on the correct side of the gears. Light sensor calibration. So some teams will have specific light sensor calibration routines to calibrate to the existing light condition. Missed line check. So a robot might know, for example, that if it has gone a certain distance and it hasn't seen a line, that it needs to go back and check for that line. Multi-sensor fusion. Rare, but also super cool. This is where you use multiple sensors at the same time to do something. Very commonly, I've seen this done with a light sensor coupled with a gyro sensor in order to go straight. So in the same way that we have a P, an I, and a D value, you can actually have additional correctional values that come from other sensors. That's usually how that's used. Auto mission restart. So auto mission restart is really interesting. So if the robot knows that it has failed a mission, for example, based on the amount of time that's left, the robot can automatically choose whether it's going to do the same mission again or whether it's going to do a different mission. So based on, some conditions, the robot will automatically restart missions, for example. VM interpreter, extraordinarily rare. This is where teams write basically their own code For example, like they might put their own code in a text file, and then the EV3 can read from that text file to do certain actions, and instead of necessarily putting everything in the directly programming language. So very rare. You're probably never going to see this. Verify port connections. So this is where the robot will actually verify that everything is connected to the correct port, like all the sensors are in the correct ports and all the motors are in the correct ports. Audio feedback and visual feedback. So this is what you think it is. This is the robots making sound in order to notify the users as to what's going on. And visual feedback is to notify, the users via some visuals of what's going on, right? So sometimes, if the robot, whenever the robot sees the line, it might make a beep, for example. That would be an audio feedback. Or if the robot, for example, detects that it's stuck, it might flash red, for example. There's also many data logging functions. Some teams use those data logging functions in order to diagnose and improve the robot. Post-run analysis. So I've seen some teams do this where if the robot's tracking what missions it's getting and things like that, the robot at the end of the match will say, the match was this long, I was picked up so many times, I got through so many attachments, stuff like that. Unique sensor use. This is just meant to be general unique sensor use. So anything you see that you think is a particularly unique use of sensors. Standard MyBlock math functions. So this is for, being able to convert, degrees to inches, for example. So for the robot, instead of saying, okay, I want the wheels to move 360 degrees, you might say, I want the robot to move 2 inches or 3 inches, for example, right? And you can do all those conversions in a standard MyBlock math function library, right? So that way you can program in terms that are much more easy to understand, and just by changing a couple of constants, you can always program directly in the distance and things that you want to program in. And then we have code here is highly modular, and code is easy to understand. So code is highly modular would be like a really good use of MyBlocks, having a lot of MyBlocks for lots of different individual functions. And code is easy to understand is, essentially good comments. Some specific praises we have for software programming are smooth movement, smooth line following, smooth use of the gyro, and smooth ultrasonic. And obviously you can just write anything else you want to write down here as well. And now we come to strategy and innovation. And strategy and innovation is one of these areas that can be a lot harder to get a good grasp on. It's probably the most subjective part of the whole robot design process, but it is certainly one of the most important. So we have the same rubric has been condensed and put on here. We have a couple of sort of general items. So maximum number of points. Obviously, that's the maximum number of points they can score. The maximum number of points is a really good indicator, generally speaking, of where a team is, right? So you'll have a lot of teams that are scoring around in the 100-point region, for example, right? But then you'll have teams that are scoring, or at least capable of scoring, in the 200 or 250 or the upper 200s or lower 300s, stuff like that. So you can get a pretty good just sort of general feel to see how many, if you ask them how many points they can get in theory. They don't actually have to achieve it. It's just how many points, if everything worked, can they get. I find that to be a great little rule of thumb. Number of sorties. So a sortie happens every time you leave base. So some teams will say we can score 350 points across 5 sorties. And they might also say here, number of attempted missions, we did 5 missions, we did 10 missions, we did 15 missions, et cetera, et cetera. These 3 questions are, I usually sort of leave these questions blank unless I feel like I really need to fill them in. But some teams spend a lot of time actually on this sort of stuff. They talk about understanding the challenges. How do you identify the challenges? How does the team discover different alternative solutions? So, the answers you can get here are completely freeform, which is why I left them all as write-ins. There's not really a good way to have a circleable answer for these. So, yeah, you'll just have to ask and see what happens. You might choose, for example, to ask one or two questions out of this battery here, just to use in a standard fashion. But sometimes a lot of this stuff they'll just tell you automatically. How does the team narrow alternatives to a few solutions? So this is a really important one, and it has a lot of different answers. So a team might say, you might ask, why did you use, how do you, if you have a lot of different options, how do you choose one, right? They might tell you points per unit time, might be based on reliability, simplicity, distance. They might choose based on difficulty. So they might choose, the easier ones or the harder ones. They might build different designs and compete them. It might be based on attainability, what the team thinks is realistic. It might be based on distance from base. It might be based on how close different things are to each other, or an attachment, or how much, monetary cost parts are, or they might have some other consistent philosophy. So, there's a whole bunch of different answers here, and most likely you'll be circling 3, 4, or 5 different things down here. So this question is sort of the follow-up. How does the team test and verify solutions? So this is after the solution has been narrowed down. How do you verify that your solution is actually doing what you want it to do? So a common way to do that is % success. So if you run 10 times in a row, everything needs to work 90% of the time. Consecutive success. This is successes in a row. So some teams might say, we need this to work 5 times in a row for us to be happy with it. And then we have highest points. So some teams will say, we will, if we run it 5 times or 10 times or whatever, we will choose the highest point value. And if that's above a certain threshold, then we'll go for it. Then there's average. So they might do 10 runs and then average the performance, and then that would be the number that they would have to decide is good enough or not. And then statistical analysis. Some teams will actually do, like stuff with standard deviations and variance and stuff like that in order to quantify, how effective their robot is. So, for example, when I did it many, many years ago, we always looked at % success and then highest points. Those were our two, the two that we always looked at. How do you decide between 2 workable solutions? How and who implements the chosen solution, and then strategy and innovation notes. So that's kind of the overall view of the sheet here. I know there's a lot. There's a lot of different things here. Also, I realized I skipped wall following up here, but that this is pretty self-explanatory, I think, because we talked about wall following a little bit later. So there's a lot of different things here, and obviously it's your choice whether you want to use this sheet or not. I usually print them out double-sided, and before any given judging session, I will try to write in all of this information on top, team number, pit number, team name, origin. I'll try to have all that stuff pre-written. And then I will, have everything nice and stacked in order, and I'll just go sheet to sheet to sheet to sheet. And, I'll have this really nice stack of sheets at the end with a very wonderful, consistent amount of information in them. So, generally speaking, this sheet will cover 99% of what you will see. Generally, the 1%, that might not be on the sheet will be extreme special cases, and you would just write them down here in your notes. Maybe even highlight them as well. So I'm always interested in feedback. So if you feel like, if you feel like you have something that you'd want to add or something you'd like to see changed in the sheet, I would really appreciate it if you would send me an email. I do have my email here on the sheet, jkinsey@gmail.com. So just give me a quick little email on anything that you think you'd like to see added or changed. I know that using the sheet in the beginning can be a little challenging because you might feel like you're not sure where things are. that's okay. You know, if you feel like the sheet is not helping you, then obviously don't use it. Just write down your notes as you would normally. But generally, you know, things are laid out in I think a fairly logical way. You know, start off with the mechanical stuff. We have a whole bunch of stuff related to the manipulators. We have the software and programming stuff, and then we have the strategy and innovation stuff. So, you know, 9 times out of 10, whatever you need is already going to be on here. So it can be very quick to circle, very quick to work on. So that's kind of my quick overview. Just other things to remember while we're judging. You know, the whole point of what we're doing here is we're not trying to interrogate the kids. We're not trying to, you know, intimidate them. We're trying to give them a positive experience with STEM. And so it's important that, you know, we remember that. You know, a lot of engineers, you know, just switch into, you know, engineering mode, and, you know, they're very critical thinkers and ask very critical questions. And sometimes for your average, you know, 10, 11 or 12-year-old kid, that can be a lot. So we want to make sure that when we're interacting with the kids, we are interacting with them in a very positive way. We want to make sure we have good eye contact. We want to make sure that we're speaking clearly, we're enunciating, you know, stuff like that. We also want to remember, like, these kids, they're like 10, 11, 12 years old, right? So just keep that in mind, that at the end of the day, they are kids. So that's just sort of my general spiel. So use this sheet to sort of objectively, you know, analyze the robot and extract information. And then you can take this sheet and use it then to help fill in points, help in deliberations, or anything else that you might need to do. And that's kind of all I got for you today. So thank you for your time and have a wonderful day. And I hope you have a wonderful first LEGO League judging experience. Bye.